In the winter of 1943, deep inside a nondescript laboratory at Wright Field in Dayton, Ohio, a team of petroleum engineers was mixing chemicals that would alter the course of the Second World War. They worked in rooms that smelled of ethyl compounds and refined hydrocarbons, spaces filled with glass beakers, distillation columns, and pressure gauges calibrated to measure what most people would never see or understand. The men in white coats weren't designing bombs or building fighters. They were hunting for something more elusive, more powerful, and far more dangerous than any weapon that could be bolted to an aircraft's wing. They were searching for fuel that could defy the laws of combustion, that could squeeze impossible power from alloy and steel, that could turn an ordinary engine into something otherworldly. And in the purple-dyed liquid they eventually created, they found it. To understand what happened in the skies over Europe in 1944 and 1945, you must first understand a simple truth that military historians often overlook. Air superiority wasn't won solely by superior tactics, better pilots, or even more advanced aircraft designs. It was won in refineries. It was won in chemical plants scattered across Texas, New Jersey, and Louisiana. It was won by men who understood molecular structures, octane ratings, and detonation pressures. The Allied victory in the air wasn't just a triumph of courage or manufacturing capacity. It was a triumph of chemistry. And at the heart of that chemical revolution was a fuel so potent, so advanced, that it gave Allied fighters a performance advantage the Luftwaffe could never match. They called it grade 150 aviation gasoline. History would remember the planes it powered, but history would largely forget the fuel itself. The story begins not in wartime, but in the laboratories of the 1930s, when engineers first began to realize that the performance ceiling of piston aircraft engines wasn't dictated by metallurgy or aerodynamics alone. It was dictated by fuel. Every pilot knew the danger of engine knock, that violent, destructive detonation that occurred when fuel ignited prematurely under compression, sending shock waves through pistons and cylinder walls. Knock wasn't just inefficient, it was catastrophic. It destroyed engines, killed pilots, and limited how much power could be safely extracted from combustion. The solution, chemists discovered, lay in the molecular structure of the fuel itself. Some hydrocarbons resisted knock better than others. Iso-octane, a branch-chain hydrocarbon with 8 carbon atoms, became the gold standard. Pure iso-octane was assigned an octane rating of 100. Everything else was measured against it. But producing iso-octane in large quantities was expensive, difficult, and required technological breakthroughs that didn't yet exist. Enter Eugene Houdry, a French mechanical engineer who immigrated to the United States in the 1930s and revolutionized petroleum refining. Houdry developed catalytic cracking, a process that used heat and specialized catalysts to break down heavy crude oil molecules into lighter, more valuable compounds. Before Houdry, refineries relied on thermal cracking, which was inefficient and produced relatively low-octane gasoline. Catalytic cracking changed everything. It allowed refiners to produce vast quantities of high-octane components, including the aromatic hydrocarbons and isoparaffins that would become the backbone of aviation fuel. Houdry's process didn't just improve fuel quality, it made high-performance fuel economically viable on an industrial scale. By the time war broke out in Europe, American refineries were already producing aviation gasoline with octane ratings of 87 and 91. Within a few years, they would be producing fuel with ratings that seemed impossible. But octane ratings alone don't tell the full story. Pure octane number measures a fuel's resistance to knock under standardized conditions, but military aircraft engines operated under anything but standard conditions. They ran at extreme altitudes where air pressure and temperature fluctuated wildly. They operated at maximum power for extended periods during combat. And they needed to deliver thrust not just consistently, but explosively on demand. To meet these requirements, petroleum engineers began experimenting with fuel blends that combined multiple high-performance components. They mixed iso-octane with toluene and xylene, aromatic hydrocarbons derived from coal tar and petroleum. They added alkylates, produced through a chemical reaction between isobutane and olefins. And crucially, they added tetraethyl lead, an organometallic compound that acted as an anti-knock agent, raising the effective octane rating far beyond what hydrocarbon chemistry alone could achieve. Tetraethyl lead was a controversial substance even in the 1940s. It was toxic, dangerous to handle, and left deposits in engines. But it worked. A few milliliters of tetraethyl lead per gallon could boost octane ratings by 10 or 15 points, allowing engines to run at higher compression ratios and higher manifold pressures without detonating. For military aviation, where every horsepower mattered, tetraethyl lead wasn't just useful, it was indispensable. American chemists pushed the concentration higher and higher, blending leaded fuel with increasingly sophisticated hydrocarbon mixtures. By the time 1943, the U.S. Army Air Forces were using 100-octane fuel as standard, a blend that had already given American fighters a measurable edge over Axis aircraft. But the engineers at Wright Field believed they could do better. Much better. The impetus for even higher performance fuel came from multiple directions. Pilots returning from combat over Europe reported that Luftwaffe fighters, particularly the Focke-Wulf FW-190 and the Messerschmitt Bf-109G, were fast, maneuverable, and deadly. American bombers flying daylight raids over Germany were being slaughtered. The 8th Air Force lost thousands of men in 1943 alone, shot down by German interceptors that could climb faster, turn tighter, and strike with devastating precision. Allied escort fighters like the Republic P-47 Thunderbolt were effective, but they lacked range. The Lockheed P-38 Lightning had range but was plagued by engine problems at high altitude. And the early versions of the North American P-51 Mustang, powered by Allison engines, were underwhelming at best. The Allies needed a fighter that could escort bombers all the way to Berlin and back, that could outrun and outfight the best the Luftwaffe had, and that could operate at altitudes where thin air turned other aircraft sluggish and unresponsive. They needed a miracle. What they got was chemistry. In early 1944, North American Aviation mated the P-51 Mustang airframe with the Packard-built Rolls-Royce engine, creating the P-51B and later the P-51D. The Merlin was a marvel of engineering, a liquid-cooled V-12 that produced smooth, reliable power, but its true potential was locked behind fuel limitations. The standard Merlin running on 100-octane fuel produced around 1,490 horsepower at maximum boost. That was impressive, but it wasn't enough. Engineers knew the Merlin could handle much more power if the fuel could support higher manifold pressures without knock, and so the chemists went back to work. They increased the isooctane content. They refined the aromatic blend. They pushed the tetraethyl lead concentration to levels that would have been unthinkable in civilian applications, and they tested endlessly in laboratories and on engine dynamometers, measuring detonation margins, exhaust temperatures, and power output under every conceivable condition. The result was grade 150 aviation gasoline, a fuel so advanced that it required a new rating system. The 150 designation didn't mean 150 octane in the traditional sense. It indicated performance equivalent to a mixture of 150% isooctane under specific lean mixture conditions. This was fuel that exceeded the theoretical limits of the octane scale. It was dyed bright purple so ground crews could instantly identify it, and it came with strict handling procedures. Engines had to be cleared for its use. Fuel systems had to be inspected. And pilots had to understand that this wasn't just high-octane gasoline. This was a substance engineered to extract power that piston engines were never designed to produce. When grade 150 fuel entered service in mid-1944, it transformed the Merlin engine. Manifold pressure could now be increased to 75 inches of mercury or higher during combat boost, compared to 61 inches on standard fuel. The result was a staggering increase in horsepower, from 1,490 to over 1,720, depending on altitude and conditions. That extra 230 horsepower changed everything. For the P-51D Mustang, grade 150 fuel was nothing short of a revelation. The aircraft's top speed jumped from around 437 miles per hour on 100-octane fuel to 448 miles per hour on 150 grade under normal conditions. But during combat boost, with manifold pressure pushed to emergency limits, the Mustang could reach speeds approaching 490 miles per hour in level flight. That made it one of the fastest piston engine fighters in the world, faster than the FW-190A, faster than the Bf-109G, and faster than nearly every Axis interceptor except the most advanced late-war jets. But speed was only part of the advantage. The extra power improved climb rate,
allowing Mustangs to reach altitude faster and intercept enemy formations before they could strike bomber groups. It improved acceleration, giving pilots the ability to close distance in pursuit or escape danger in a dive. And it improved endurance, because the Merlin running on 150-grade fuel was more efficient at cruise power, burning less fuel to maintain speed. The Mustang already had exceptional range thanks to its laminar flow wing and internal fuel capacity. With 150-grade fuel, it became the only Allied fighter capable of escorting bombers from England to Berlin and back, engaging Luftwaffe interceptors over the target, and still having fuel to spare. The impact on the air war was immediate and devastating. When P-51 Mustangs powered by grade 150 fuel began escorting 8th Air Force bombers in the spring and summer of 1944, Luftwaffe losses skyrocketed. German pilots, accustomed to attacking lumbering bombers with minimal fighter opposition, suddenly found themselves facing a fighter that could outrun them, outclimb them, and outlast them. The Mustang's combination of speed, altitude performance, and range meant that no Luftwaffe base, no airfield, no target in Germany was safe. Allied fighters could loiter over enemy territory for hours hunting for targets of opportunity. They could strafe airfields, destroy aircraft on the ground, and intercept German fighters as they attempted to take off or land. The Luftwaffe, already bleeding from attrition and fuel shortages, was being systematically annihilated. And much of that destruction was made possible by a fuel that German chemists could not replicate. The Luftwaffe fuel problem was both technical and logistical. Germany, lacking access to abundant oil reserves, relied heavily on synthetic fuel production, primarily through the Fischer-Tropsch process, which converted coal into liquid hydrocarbons. This process produced usable fuel, but the quality was inferior. German synthetic gasoline had lower aromatic content and poorer anti-knock characteristics than Allied fuel. Even with the addition of lead compounds, Luftwaffe aviation fuel typically rated between 87 and 96 octane, far below the 100 octane standard used by the Allies, and nowhere near the 150-grade fuel powering the P-51. This disparity meant that German engines had to run at lower compression ratios and lower manifold pressures to avoid destructive knock. The result was less power, lower speeds, and reduced altitude performance. German engineers tried to compensate with turbochargers, nitrous oxide injection systems, and advanced supercharger designs. But these solutions added weight, complexity, and maintenance requirements. Meanwhile, Allied pilots simply poured purple fuel into their tanks and pushed the throttle forward. The chemical engineering behind grade 150 fuel was a collaborative effort that spanned multiple institutions and industries. Standard Oil of New Jersey played a leading role, leveraging its expertise in catalytic cracking and alkylation to produce the high-octane components needed for advanced blends. Shell Oil contributed research into aromatic hydrocarbons, particularly toluene and xylene, which were critical for boosting performance at high altitudes. The Ethyl Corporation, which held patents on tetraethyl lead production, worked closely with military engineers to optimize lead concentrations for maximum anti-knock effect without excessive engine deposits. And at Wright Field, the Army Air Force's Research Center, engineers conducted exhaustive testing on prototype fuels, measuring their performance in captured German engines, British Merlins, and American radials. Every batch of fuel was analyzed for volatility, calorific value, freezing point, and detonation characteristics. Nothing was left to chance. General Jimmy Doolittle, the famed aviator and aeronautical engineer, was one of the earliest advocates for high-octane fuel. In the 1930s, Doolittle had conducted pioneering research into fuel chemistry while working for Shell Oil, demonstrating that higher octane ratings translated directly into improved aircraft performance. When he took command of the 8th Air Force in early 1944, Doolittle pushed aggressively for the adoption of grade 150 fuel, arguing that it would give his fighters a decisive edge over the Luftwaffe. His advocacy paid off. By mid-1944, 150-grade fuel was flowing to frontline units in Europe, and the results exceeded even optimistic predictions. Test pilots at Wright Field reported power increases of 25 to 30% compared to 100-octane fuel, with no significant increase in engine wear or failure rates when operated within approved parameters. The fuel's only drawback was cost and production complexity, but in the calculus of total war, such considerations were irrelevant. If purple fuel could save a single bomber crew, it was worth every dollar. The Royal Air Force also adopted 150-grade fuel for its Spitfires and Mustangs during Operation Overlord, the Allied invasion of Normandy. British pilots flying Spitfire Mark 9 engines equipped with Merlin 66 engines found that the high-performance fuel allowed them to match the speed and climb rate of the latest German fighters, including the Bf 109 G6 and the FW 190A8. RAF Mustang 3s, the British designation for the P-51B and C models, achieved similar performance gains, enabling them to provide long-range escort for RAF bomber groups' daylight raids into occupied France and Germany. The fuel's purple color became a symbol of Allied technological superiority, a visible reminder that the chemistry labs of America and Britain were winning a war that most soldiers would never see. Ground crews knew to handle it with care, pilots knew it gave them an edge, and German intelligence officers, analyzing captured fuel samples, knew that they were facing an adversary with resources and scientific capabilities they could not match.
But fuel technology wasn't just about raw performance. It was about logistics, about the ability to produce and distribute millions of gallons of high-performance gasoline to air bases scattered across England, North Africa, Italy, and the Pacific. This required a supply chain of staggering complexity, involving refineries, tanker ships, pipelines, storage depots, and fuel trucks. The Allies built this infrastructure with ruthless efficiency, coordinating production schedules across dozens of refineries, shipping fuel in convoys protected by destroyers and escort carriers, and establishing fuel depots close to operational airfields. By 1944, the United States was producing over 50 billion gallons of petroleum products per year, a significant portion of which was aviation gasoline. Germany, by contrast, struggled to produce even a fraction of that amount, and much of its synthetic fuel production was targeted by Allied bombers. Refineries in Ploesti, Romania, and synthetic fuel plants scattered across the Ruhr were systematically destroyed, crippling the Luftwaffe's ability to operate. Even when German pilots had aircraft, they often lacked the fuel to fly them. The human cost of this chemical arms race is difficult to quantify, but it was profound. Every gallon of grade 150 fuel represented countless hours of research, testing, and refinement. It represented the labor of refinery workers, tanker crews, and ground personnel who handled dangerous chemicals in all weather conditions. And it represented the lives saved by giving Allied pilots a technological edge that kept them alive long enough to return home. When a P-51 pilot pushed his throttle to combat boost and felt his Merlin engine surge to 1,720 horsepower, he was experiencing the culmination of years of scientific effort. He was riding a wave of innovation that stretched back to Houdry's catalytic cracking process, to Doolittle's octane research, to the chemists at Standard Oil who mixed compounds in laboratories far from the sound of gunfire. He was, in effect, weaponizing chemistry, turning petroleum into power and power into survival. German aces, men like Günther Röhrl, who flew the Bf 109 and survived the war with 275 confirmed kills, spoke with grudging respect for the P-51 Mustang. Röhrl would later recall that the Mustang's combination of speed, range, and altitude performance was a formidable opponent, one that could dictate the terms of engagement and disengage at will. German pilots flying on low-octane synthetic fuel found themselves at a distinct disadvantage. They couldn't run, they couldn't climb as fast, and they couldn't sustain high power settings without risking engine failure. The psychological impact was devastating. Whenever encounter with a Mustang meant fighting an aircraft with superior performance, when every mission might be your last because you simply couldn't escape, morale crumbled. The Luftwaffe's pilot training programs, already decimated by losses and fuel shortages, couldn't produce replacements fast enough. By late 1944, the average German fighter pilot had fewer than 50 hours of flight time. Their American counterparts often had 200 hours or more. And they were flying aircraft powered by fuel that gave them every advantage. The technical specifications of grade 150 fuel revealed the sophistication of its formulation. The base blend consisted of approximately 70% isooctane and alkylate, both of which are highly resistant to knock.
To this base, refiners added around 20% aromatic hydrocarbons, primarily toluene and xylene, which not only improved anti-knock properties, but also increased the fuel's energy density, providing more power per gallon. The remaining 10% consisted of additives, including tetraethyl lead at concentrations of 4 to 6 milliliters per gallon, along with oxidation inhibitors to prevent gum formation during storage, corrosion inhibitors to protect fuel system components, and fuel dyes for identification. The resulting mixture had a research octane number exceeding 130, though the exact rating varied depending on the specific blend. More importantly, it had a motor octane number, which measures performance under high-temperature, high-speed conditions. That was equally impressive. This dual rating system ensured that the fuel performed well under both cruise conditions and combat boost. The purple dye used to identify grade 150 fuel was more than just a safety measure. It was a symbol. To pilots and ground crews, purple fuel meant maximum performance, the best their nation's chemists could produce. It meant they were flying with every possible advantage. And it meant that someone, somewhere, was thinking about their survival. The dye itself was typically a mixture of synthetic organic compounds, chosen for their stability and visibility. It didn't affect the fuel's performance, but it prevented misfueling accidents, which could be catastrophic. An engine designed to run on 150-grade fuel would perform poorly and might even suffer damage if accidentally filled with lower-octane gasoline. Conversely, an engine not cleared for 150-grade fuel could be destroyed by the higher manifold pressures it enabled. The purple color eliminated ambiguity. If the fuel was purple, you knew exactly what you were dealing with. Testing procedures for grade 150 fuel were rigorous and exhaustive. Before any batch was approved for operational use, samples were analyzed in laboratory-grade octane engines, devices that simulated the conditions inside an aircraft engine. Chemists measured knock onset under varying temperatures, pressures, and air-fuel ratios. They tested for vapor lock, a condition where fuel vaporizes prematurely in the fuel lines, causing engine starvation. They checked freezing points to ensure the fuel remained liquid at high altitudes where temperatures could drop to minus 40 degrees Fahrenheit or lower. They analyzed combustion products to ensure that lead deposits wouldn't foul spark plugs or damage valves. And they conducted endurance tests, running engines continuously on the fuel for hundreds of hours to detect any long-term degradation or reliability issues. Only after a fuel batch passed every test was it shipped to operational units. This level of quality control was unprecedented in military logistics, but it was necessary. A single batch of bad fuel could ground an entire squadron.
The impact of grade 150 fuel extended beyond the P-51 Mustang. Other Allied fighters also benefited, though to varying degrees. The P-47 Thunderbolt, powered by the massive Pratt & Whitney R2800 radial engine, gained additional horsepower and improved high-altitude performance when running on 150-grade fuel. The P-38 Lightning, with its twin Allison V1710 engines, saw improvements in climb rate and speed, though it remained less effective at high altitude due to turbocharger inefficiencies. The British Hawker Tempest and the Supermarine Spitfire Mk-14, both powered by Napier Sabre or Griffin engines, achieved remarkable performance on high-octane fuel, becoming some of the fastest piston fighters of the war. Even bombers benefited indirectly. The B-17 Flying Fortress and B-24 Liberator didn't use 150-grade fuel themselves, but they were protected by fighters that did, and that protection allowed them to complete their missions and return home. The entire Allied air campaign in Europe was built on a foundation of fuel chemistry. By the fall of 1944, the strategic situation over Europe had shifted irreversibly in favor of the Allies. The Luftwaffe, once a fearsome and dominant force, was now a shadow of its former self. Fuel shortages grounded hundreds of aircraft, experienced pilots were dead or captured, and the few who remained were flying aircraft that couldn't match the performance of Allied fighters. The introduction of German jet aircraft, including the Messerschmitt Me-262, represented a desperate attempt to regain air superiority through technology. The Me-262 was indeed fast, capable of speeds over 540 miles per hour, but it suffered from short endurance, unreliable engines, and vulnerability during takeoff and landing.
P-51 Mustangs, loitering near German airfields, ambushed Me-262s as they attempted to land, shooting them down before they could pose a threat. The jet age had arrived, but piston-engine fighters, powered by Grade 150 fuel, remained dominant. Speed alone wasn't enough. It took speed, range, reliability, and numbers. And in 1944, the Allies had all four. The production of Grade 150 fuel was a triumph of American industrial capacity. Refineries operated around the clock, processing crude oil into the specialized components needed for high-octane blends. The alkylation units that produced alkylate, a key component, required precise temperature and pressure control along with sulfuric acid or hydrofluoric acid catalysts. These were dangerous, complex operations that demanded skilled workers and constant maintenance. Catalytic cracking units, which produced high-octane gasoline from heavier crude fractions, operated at temperatures exceeding 900 degrees Fahrenheit, with catalysts that had to be regenerated continuously to maintain activity. And the distillation towers that separated crude oil into its various components were marvels of chemical engineering, standing hundreds of feet tall and processing thousands of barrels per day. The fact that this entire industry could pivot to wartime production, could scale up to meet military demands, and could maintain quality standards under pressure is a testament to the organizational and technical capabilities of the Allied nations. The relationship between fuel chemistry and engine design was symbiotic. As fuel quality improved, engine designers could push their creations to higher performance levels. The Merlin engine, for example, underwent continuous refinement throughout the war, with each new variant incorporating stronger components, improved cooling systems, and higher compression ratios. These improvements were only possible because fuel technology kept pace. An engine designed to run on 150-grade fuel required stronger connecting rods, pistons capable of withstanding higher temperatures and pressures, and valve seats that could resist the corrosive effects of lead deposits. Rolls-Royce and Packard engineers worked closely with fuel chemists, sharing data and coordinating development efforts. This collaboration ensured that when 150-grade fuel became available, engines were ready to use it. The result was a virtuous cycle of improvement, where better fuel enabled better engines, which in turn demanded even better fuel. The logistical challenge of distributing Grade 150 fuel across the European theater was monumental. Fuel had to be transported by tanker from American refineries to British ports, a journey fraught with danger from German U-boats. Once in Britain, it was stored in underground tanks at dozens of airfields scattered across East Anglia, the Midlands, and southern England. From there, fuel trucks delivered it to individual aircraft, with ground crews carefully monitoring quantities to ensure each plane received the correct load for its mission. Every link in this chain had to function flawlessly. A single bottleneck, a single tanker sunk, a single fuel depot destroyed could ground entire fighter groups. The Allies protected this supply chain with the same intensity they protected bomber formations. Convoys were escorted, depots were camouflaged and defended, and backup supplies were stockpiled at multiple locations. The Germans understood the importance of fuel logistics and targeted Allied fuel supplies whenever possible, but they lacked the resources to disrupt the flow significantly.
In the Pacific theater, the story of aviation fuel was somewhat different, but no less important. American fighters like the Grumman F-6F Hellcat and the Vought F-4U Corsair were powered by massive radial engines that thrived on high-octane fuel. The Pratt & Whitney R2800, which powered the Corsair, produced over 2,000 horsepower when running on 100-octane fuel, and even more with water methanol injection. While 150-grade fuel was less common in the Pacific due to logistical constraints, the availability of 100-octane fuel gave American naval aviators a decisive edge over Japanese opponents. Japanese aircraft, constrained by limited access to high-quality petroleum and reliance on lower-octane fuels, struggled to match American performance. The result was a slaughter. By 1944, Japanese pilots were flying aircraft that were slower, less maneuverable at high speed, and less durable than their American counterparts. Fuel chemistry once again tipped the scales. The end of the war in Europe came in May 1945 with the unconditional surrender of Nazi Germany. By that point, the Luftwaffe had effectively ceased to exist. What few aircraft remained were grounded for lack of fuel, spare parts, and trained pilots. The Allied air forces, meanwhile, were at the peak of their power, equipped with thousands of fighters and bombers, all fueled by the highest quality aviation gasoline ever produced. The final months of the war saw Allied fighters ranging freely over Germany, attacking trains, trucks, tanks, and any remaining pockets of resistance. The P-51 Mustang, powered by grade 150 fuel, flew some of the longest missions of the war, escorting bombers to targets deep in Bavaria and Austria, then strafing airfields on the return journey. The fuel that made these missions possible was a weapon as powerful as any bomb or bullet.
The war also accelerated research into alternative fuels and synthetic processes. While the Allies relied primarily on natural petroleum, they invested heavily in understanding how to produce fuel from other sources if necessary. The Germans, as mentioned, relied on coal gasification and the Fischer-Tropsch process. The British experimented with coal hydrogenation. The Americans explored everything from alcohol-based fuels to synthetic alkylates. These efforts didn't always result in practical wartime applications, but they laid the foundation for post-war energy research. The techniques developed during the war informed the creation of synthetic lubricants, the refinement of jet fuel, and even the propellants used in rockets and missiles. The space race, which began less than a decade after the war's end, was built on chemistry and engineering principles that had their roots in the aviation fuel research of the 1940s. By the time the war ended in the Pacific in August 1945, the world had changed irrevocably. The atomic bomb, which brought about Japan's surrender, overshadowed every other technological achievement of the war. But the development of high-octane aviation fuel was no less significant. It was simply quieter, less dramatic, less immediate in its impact. There was no mushroom cloud, no instant annihilation. Just a steady, relentless improvement in aircraft performance, a gradual shifting of the balance of power, a slow strangling of the enemy's ability to fight. The chemists who created Grade 150 fuel saved thousands of lives, not through a single decisive blow, but through incremental advantages that accumulated over time. Every mission that succeeded because a pilot could fly faster, climb higher, or stay airborne longer was a victory for chemistry. Every bomber crew that returned home because their escorts could engage the enemy on favorable terms owed their survival to fuel as much to firepower. In the decades since the war, aviation has evolved beyond recognition. Piston engines have given way to jets, and jets have given way to turbofans. The roar of a Merlin engine has been replaced by the scream of a turbine. But the fundamental principles remain the same. Performance is still dictated by energy density, by combustion efficiency, by the ability to extract maximum power from fuel. Modern jet fuel, such as JP-8, used by the U.S. military, is a descendant of the aviation gasoline developed during World War II. It uses different hydrocarbons, different additives, and different refining processes, but the goal is identical: to provide reliable, high-energy fuel that enables aircraft to perform at their best. The chemists who work on jet fuel today are the intellectual heirs of the men who created Grade 150 gasoline. They face different challenges, work with different technologies, and operate in a world transformed by the very conflict their predecessors helped to win. But the mission remains unchanged: to give pilots every possible advantage, to squeeze every ounce of performance from their machines, to ensure that when metal meets sky, chemistry is on their side. The legacy of Grade 150 fuel extends into unexpected corners of history. After the war, surplus stocks of high-octane aviation gasoline found their way into civilian hands, where hot rodders and racing enthusiasts discovered its potential. The fuel that had powered Mustangs over Berlin now powered modified cars on dry lake beds in California, setting land speed records and spawning a culture of performance that would eventually become mainstream. The octane wars of the 1950s and 1960s, when gasoline companies competed to offer the highest octane ratings to consumers, were a direct echo of the military fuel competition of the 1940s. Terms like high test and premium entered the popular vocabulary, though few consumers understood that they were the beneficiaries of wartime research. The aviation fuel chemists had, without intending to, revolutionized civilian transportation as well. Environmental concerns eventually ended the use of tetraethyl lead in automotive gasoline. By the 1970s, the toxic effects of lead emissions were well documented, and governments around the world began phasing out leaded fuel. Aviation fuel, however, continued to use lead for decades longer, and in some applications still does. Small piston engine aircraft, the kind flown by private pilots and flight schools, often run on 100 LL fuel, where LL stands for low lead.
It's a direct descendant of the fuels developed during World War II, modified and refined, but fundamentally similar. The purple dye is gone, replaced by blue, but the chemistry remains recognizable. These aircraft, humming along at a few thousand feet, are flying on technology that won a war 3/4 of a century ago. It's a testament to how effective that technology was and how difficult it has been to replace it entirely. The human stories behind Grade 150 fuel are largely forgotten, buried in classified reports and technical journals that few people will ever read. The chemists who spent years perfecting hydrocarbon blends, the refinery workers who operated dangerous equipment in pursuit of higher octane ratings, the logistics personnel who ensured that fuel reached the right places at the right times, these individuals are anonymous heroes of a conflict where heroism is usually measured in aerial victories and medals. Their contribution was no less vital. Without them, the P-51 Mustang would have been just another fighter, effective but not revolutionary. Without them, the 8th Air Force's daylight bombing campaign might have failed, costing countless more lives and prolonging the war. Without them, the balance of air power might have remained contested, allowing the Luftwaffe to inflict far greater damage. They worked in obscurity, mixing chemicals and analyzing data, and in doing so, they changed the course of history. There were, of course, failures and setbacks along the way. Not every fuel blend worked as intended. Some caused excessive engine wear, others proved unstable in storage, forming gums and sediments that clogged fuel systems. Still others froze at high altitude or vaporized prematurely, causing vapor lock. Each failure was analyzed, understood, and corrected. The process was iterative, a constant cycle of testing, refinement, and retesting. The engineers at Wright Field maintained detailed logs of every test, recording manifold pressures, cylinder head temperatures, exhaust gas temperatures, and power output under varying conditions. These logs, thousands of pages of handwritten data, formed the empirical foundation for fuel development. They weren't elegant or exciting. They were just numbers, measurements, observations. But those numbers represented lives saved and battles won.
The psychological dimension of fuel superiority should not be underestimated. When Allied pilots knew they had better fuel, better engines, and better performance, they flew with confidence. They could press attacks, knowing they had the power to disengage if necessary. They could escort bombers deep into enemy territory, knowing their aircraft had the range and endurance to complete the mission. And they could face Luftwaffe interceptors without fear, knowing that in most cases they had the superior machine. That confidence translated into aggressive tactics, better situational awareness, and higher kill ratios. Conversely, Luftwaffe pilots, aware that their aircraft were outperformed, flew defensively. They conserved fuel, avoided prolonged engagements, and retreated when faced with superior numbers or performance. The mental burden of knowing that the enemy had every advantage was corrosive. It bred caution, hesitation, and ultimately defeat. The cost of developing and producing Grade 150 fuel was substantial, though exact figures are difficult to determine. The investment in research alone ran into millions of dollars, a significant sum in 1940s currency. The construction of new refinery units, the modification of existing facilities, and the logistics of distribution added billions more. But in the context of a war that cost the United States over $4 trillion in current dollars, the investment in aviation fuel was a rounding error. And the return on that investment was incalculable. How do you measure the value of air superiority? How do you quantify the lives saved by giving pilots a faster, more capable aircraft? How do you calculate the strategic advantage of being able to strike targets anywhere in enemy territory with impunity? The economists who analyze military spending can produce cost-benefit ratios, but they can never fully capture the intangible benefits of technological superiority. As the war progressed, the gap between Allied and Axis fuel technology widened. By 1945, American refineries were producing not just Grade 150 fuel, but experimental blends with even higher performance characteristics. Some of these fuels, designated Grade 160 or Grade 170, never saw widespread operational use because the war ended before they were needed. But they existed, proof that the Allied fuel chemists were always thinking ahead, always planning for the next challenge. The Germans, meanwhile, were regressing.
By the final months of the war, Luftwaffe aircraft were sometimes forced to fly on low-grade fuels intended for vehicles, fuels that caused severe engine knock and reduced power output. Pilots reported that their engines ran rough, overheated quickly, and lost power at critical moments. It was a humiliating end for an air force that had once dominated European skies. The story of Grade 150 fuel also intersects with the broader narrative of American industrial mobilization during World War II. The same nation that built tens of thousands of aircraft, hundreds of ships, and millions of tons of munitions also transformed its petroleum industry into the most advanced in the world. This wasn't accidental. It was a result of deliberate policy decisions, of government investment in research and infrastructure, of collaboration between public and private sectors. The Office of Scientific Research and Development, established in 1941, coordinated much of the research into military technologies, including aviation fuel. Universities, corporations, and government laboratories worked together, sharing information and resources in ways that would have been impossible in peacetime. The result was an innovation ecosystem that produced breakthroughs at an astonishing pace. Grade 150 fuel was just one of many successes, but it was emblematic of a larger pattern. There is also a darker side to the story, one that involves environmental damage and worker safety. The production of high-octane fuel required the use of toxic chemicals, including sulfuric acid, hydrofluoric acid, and tetraethyl lead. Workers in refineries and chemical plants were exposed to these substances daily, often with inadequate protective equipment. Many suffered health problems as a result, including lead poisoning, chemical burns, and respiratory diseases. The environmental impact was also significant. Refineries discharge waste products into rivers and in the air, contributing to pollution that would take decades to remediate. In the urgency of wartime production, safety and environmental concerns were often secondary to output and efficiency. This isn't to diminish the achievement of the fuel chemists, but to acknowledge that their work, like all wartime production, came at a cost that extended beyond dollars and cents. The international dimension of fuel technology is also worth considering. The British, with their own advanced petroleum industry, contributed significantly to the development of high-octane fuels. The Asiatic Petroleum Company, a subsidiary of Royal Dutch Shell, conducted pioneering research into aromatic hydrocarbons. British refineries produced 100-octane fuel earlier than their American counterparts, and by 1940, the Royal Air Force was using it extensively. The Anglo-American cooperation in fuel development was formalized through various committees and working groups, ensuring that research findings were shared and production standards were harmonized. This collaboration extended to other allied nations as well. Canadian refineries produced aviation fuel for the RAF and the RCAF. Soviet pilots, flying American-built aircraft under Lend-Lease, used American fuel. The global nature of the fuel supply chain was a microcosm of the Allied war effort itself, diverse, interconnected, and greater than the sum of its parts. Comparing Allied fuel technology to that of other combatants reveals stark disparities. The Japanese, constrained by limited access to crude oil and forced to rely on supplies from conquered territories, never developed fuel chemistry comparable to the Allies. Japanese aviation gasoline typically rated between 87 and 92 octane, adequate for early war aircraft but insufficient for the high-performance fighters that emerged later. Japanese pilots flying against American aircraft in 1944 and 1945 were at a severe disadvantage, not just in pilot training and aircraft numbers, but in basic performance. The Mitsubishi A6M0, famous for its maneuverability and range, was powered by a Sakai engine that produced only 1,130 horsepower, less than two-thirds the output of a Merlin running on grade 150 fuel. The Zero couldn't climb as fast, couldn't dive as steeply, and couldn't sustain high speeds. Engineers tried to compensate for lightweight construction and superior maneuverability, but these advantages were negated when faced with faster and more powerful American fighters. The Italian Air Force, the Regia Aeronautica, faced similar challenges. Italy's petroleum industry was small and underdeveloped, and the nation relied heavily on imported fuel. When Allied blockades cut off those supplies, Italian pilots were forced to conserve fuel, reducing training hours and limiting operational sorties. The Mach-E C-202 Folgore, one of Italy's better fighters, was powered by a license-built version of the German Daimler-Benz DB601 engine, which required high-octane fuel to operate at peak performance. When such fuel wasn't available, the Folgore's performance suffered. By the time Italy surrendered in 1943, its air force was a spent force, unable to contest Allied air superiority over the Mediterranean. Fuel scarcity was one of many factors contributing to this collapse, but it was a significant one.
The technical specifications of the Packard Merlin V16507, the engine that powered the P-51D Mustang, illustrate the importance of fuel quality. This engine had a displacement of 27 liters, a compression ratio of 6.0 to 1, and used a two-stage, two-speed supercharger to maintain power at high altitude. At sea level, running on grade 150 fuel at maximum boost, it produced 1,720 horsepower. At 25,000 feet, where the supercharger compensated for thin air, it still produced over 1,500 horsepower. This altitude performance was critical for intercepting high-flying bombers or engaging enemy fighters in the stratosphere. The Merlin's reliability was equally impressive. Engines often ran for hundreds of hours between overhauls, a testament to the quality of both the engineering and the fuel. Pilots trusted the Merlin implicitly, knowing that it would deliver power when needed and bring them home safely. The cultural impact of the P-51 Mustang, powered by its revolutionary fuel, extended far beyond the war. The aircraft became an icon, a symbol of American ingenuity and air power. It appeared in movies, books, and television shows, always portrayed as the hero's machine, sleek and deadly. Restored Mustangs still fly today at air shows, delighting crowds with their distinctive sound and graceful lines. But few spectators realize that the performance they're witnessing is only possible because of fuel technology developed 8 decades ago. The Mustangs at air shows typically run on 100 LL avgas, not grade 150, but the lineage is clear. Every time a restored Mustang roars down a runway and leaps into the sky, it's a living tribute to the chemists and engineers who made such performance possible. The strategic implications of fuel superiority extended beyond tactical combat. The ability to conduct long-range escort missions meant that Allied bombers could strike targets deep in Germany with acceptable losses. This strategic bombing campaign, while controversial in its execution and effectiveness, undeniably diverted German resources. Factories, rail yards, and oil refineries were destroyed, forcing Germany to disperse production and invest in air defenses. Thousands of anti-aircraft guns that might have been used on the Eastern Front were instead deployed to defend German cities. Hundreds of fighters that could have supported ground operations were tied up in homeland defense, and the Luftwaffe's best pilots, who might have decimated Soviet air forces, were instead shot down over their own country by P-51 Mustangs powered by purple fuel. The second-order effects of fuel technology rippled through the entire strategic landscape of the war. There's also a philosophical question worth pondering. What does it mean that chemistry won the air war? In a sense, it's a validation of the Enlightenment project, the belief that knowledge and reason can overcome brute force. The Allies didn't defeat the Luftwaffe solely through courage or numbers, though both played a role. They defeated it through understanding, through the patient accumulation of scientific knowledge and the rigorous application of that knowledge to practical problems. The chemists who developed grade 150 fuel were engaged in a form of intellectual combat, a battle fought with equations and experiments rather than bullets and bombs. And they won decisively. This suggests that in modern warfare, and perhaps in all human endeavors, the side that invests in education, research, and innovation will prevail. It's a hopeful message in a way, even if the context is war. The transition from wartime to peacetime production was not seamless. After the war ended, demand for aviation fuel plummeted. Refineries that had operated at maximum capacity for years suddenly found themselves with excess production. Some facilities were mothballed, others were converted to produce automotive gasoline and heating oil. The chemists and engineers who had developed military fuels shifted their focus to civilian applications. Some went to work for oil companies, continuing their research into fuel chemistry. Others joined universities, where they trained a new generation of petroleum engineers. And a few went into government service, advising on energy policy and strategic petroleum reserves. Their expertise, forged in the crucible of war, found new applications in a world slowly transitioning to peace. The environmental legacy of wartime fuel production is still visible today. Some refinery sites from the 1940s are now Superfund sites, contaminated by decades of chemical use and requiring extensive cleanup. The same substances that made grade 150 fuel so effective, tetraethyl lead, aromatic hydrocarbons, and various solvents, also left lasting scars on the landscape. Soil and groundwater contamination in communities near refineries had led to health problems and expensive remediation efforts. This is part of the hidden cost of the war, a cost borne by communities that had little say in the matter. Acknowledging this legacy doesn't diminish the achievement of the fuel chemists, but it does provide a more complete picture of what was sacrificed in the pursuit of victory.
The story of grade 150 fuel is, in many ways, a story about the price of progress. Every technological advance carries with it unintended consequences, costs that aren't always apparent at the time. The chemists who developed high-octane fuel were focused on winning a war, on saving lives, on defeating an enemy that threatened civilization itself. They succeeded brilliantly, but their success came at a cost: environmental damage, worker health problems, and the creation of a toxic substance that would take decades to phase out. This isn't a condemnation. It's simply recognition that progress is complex, that achievements are rarely pure, and that history judges us not just by what we accomplished, but by what we left behind. As we look back on the development of grade 150 aviation fuel from the perspective of the 21st century, we can appreciate both its brilliance and its limitations. The fuel itself was a masterpiece of chemical engineering, a substance that pushed the boundaries of what was possible. But it was also a product of its time, relying on technologies and materials that we now know to be problematic. Modern fuel chemistry has moved beyond leaded gasoline, beyond the heavy reliance on aromatic hydrocarbons toward cleaner, more efficient alternatives. Jet fuel, biofuels, and even hydrogen are replacing the petroleum products that dominated the 20th century. Yet the fundamental principles remain the same: understand the chemistry, optimize the blend, and deliver maximum performance. The chemists of World War II would recognize the challenges their modern counterparts face, even if the specific solutions have evolved. The human drama of wartime fuel development deserves more recognition than it has received. These were not faceless bureaucrats or anonymous technicians. They were individuals with families, with hopes and fears, with the knowledge that their work directly impacted the survival of young men flying over hostile territory. Every batch of fuel they produced, every test they conducted, every improvement they made could mean the difference between a pilot returning home or being shot down. That burden must have been immense, yet they carried it day after day, mixing compounds and analyzing data, driven by a sense of duty and the knowledge that they were part of something larger than themselves. Their contribution to the Allied victory deserves to be remembered alongside the more visible achievements of soldiers, sailors, and airmen. In the final accounting, the development of grade 150 aviation fuel represents one of the most significant technological achievements of World War II. It wasn't as dramatic as the atomic bomb, as visible as the aircraft carriers, or as celebrated as radar, but it was, in its own way, just as important. It gave the Allies a decisive advantage in the air war, an advantage that translated into strategic bombing success, tactical air superiority, and ultimately victory. The purple fuel that flowed through the tanks of P-51 Mustangs was more than a chemical mixture. It was a symbol of industrial might, scientific excellence, and the determination to win at all costs. It was proof that wars are won not just on battlefields, but in laboratories, refineries, and in the minds of people who understand that knowledge is power. The chemists who created purple fuel understood this, even if they couldn't articulate it. They knew that their work mattered, that it would save lives and hasten victory. And they were right. The legacy of that fuel lives on, not in museums or monuments,
but in the aircraft that still fly, in the petroleum industry that still refines fuel according to principles developed during the war, and in the culture of innovation that continues to drive progress. Every time a modern fighter jet screams across the sky, burning fuel optimized for maximum thrust and efficiency, it carries with it the inheritance of those wartime chemists. Every time a commercial airliner crosses an ocean powered by carefully engineered jet fuel, it benefits from research that began in a desperate race to outperform the enemy. And every time an engineer sits down to solve a problem involving energy, combustion, or performance, they're following a path first traced by men and women who understood that chemistry could change the world. The P-51 Mustang may have been the sword, but grade 150 fuel was the hand that wielded it, the invisible force that made the weapon deadly. Without that fuel, the Mustang would have been just another aircraft, competent but not exceptional. With it, the Mustang became a legend, a machine that could outfight anything the Luftwaffe could put in the air. And in that transformation lies a lesson that extends far beyond aviation, far beyond war. It's a lesson about the power of innovation, about the importance of investing in science and research, and about the reality that knowledge and understanding are the ultimate multipliers. The chemists who created purple fuel understood this, even if they couldn't articulate it. They knew that their work mattered, that it would save lives and hasten victory. And they were right.
The sky above Europe in 1944 was a battlefield unlike any the world had seen before. Thousands of aircraft locked in combat, contrails edging paths across the stratosphere, the roar of engines and the chatter of machine guns echoing for miles. In that chaos, in that violence, chemistry was a silent partner, invisible but omnipresent. Every Allied pilot who pushed his throttle forward, every Mustang that climbed toward the sun, every escort mission that succeeded owed something to the purple fuel in the tanks. It was the hidden variable, the secret ingredient, the advantage that the enemy could see but never match. And when the war finally ended, when the guns fell silent and the aircraft returned to their bases for the last time, that fuel had done its job. It had helped win the air war. It had helped win the war itself. And in doing so, it had changed the world forever. The final victory of grade 150 fuel wasn't measured in aerial kills or sorties flown. It was measured in possibilities realized, in potential unleashed, in the transformation of an aircraft from very good to absolutely dominant. It was the difference between contesting the skies and owning them, between hoping for air superiority and achieving it with mathematical certainty. The purple fire that burned in those Merlin engines wasn't magic, it was science, applied with precision and purpose, refined through countless hours of research and testing, delivered through an industrial supply chain of staggering complexity. It was humanity's ability to understand nature, to manipulate chemistry for its own ends, and to wield that knowledge as a weapon. In the end, the Allies didn't just outfight the Axis, they outthought them, out-innovated them, and out-engineered them. And nowhere was that triumph more evident than in the fuel that powered their finest aircraft to victory.